honor and pleasure to welcome today at our Monday seminar and FJelinekSeries two outstanding scholars from the United States, Professor Sergei Nirenburg and Professor McShane from the Polytechnic Institute in Troy, in New York. And well, I think that I don't need to introduce them here. Only I would like to say that with Sergei we share the membership in the International Committee for Computational Linguistics. I can't even remember since when we know each other, but it's very, very long ago, and not only from the United States. And I think this is really a topic which is very, very suitable for the interdisciplinary audience here, namely linguistics for the age of artificial intelligence. So, thank you very much for coming, and the floor is yours.
Thank you very much, Eva. It's great to be here. It's my first time that I lecture in your department, and well, this is an honor. So, about the topic, first of all, apologies that the title that we sent around beforehand was somewhat different, but the issue here is that this is the title of a book that we have almost finished and hope to publish soon. And what we will be talking about is, as it says here, natural language understanding integrated into multifunctional intelligent agents. So we're, in our parlance between the two of us, we're not doing natural language processing, we're doing natural language understanding. There is a difference, so to us. And I think that probably most of you don't do the things in your work the way we are doing it, but we will try to introduce that's why we want to introduce kind of the background of why it is that we are doing what we are doing and what it is. So we are working on what we call language-endowed intelligent agents, or layers. Our lab at RPI is called the Layer Lab, and we develop them within something that is called the cognitive architecture. People know the concept of cognitive architectures? No. So, okay, so this is the foundation for building intelligent agents that do not just language but other things too, with the idea of modeling the way people do it. You see, there is a big difference between doing applications so that there is a given task that is done by whatever means, well or not so well, but in whatever way, and the added complication of trying to do it the way people do it. By the way, I do realize that this is a very complex matter in itself. What does it mean to have systems that do things the way people do it? I would be more than happy to discuss that issue afterwards in the question period. But first, what we will do is this. There are two of us, so what I will do, I will frame our research program, and then Marge will actually tell you about the real stuff related to language. Okay, so without further ado. So the top-level goals of our research and development, and by the way, we have been at it for many, many years under different in different guises. Developing human-level language-endowed intelligent agents. This is actually the original goal of AI, but AI these days has changed. So for us, agent must be viewed as eventually as colleagues and not just as orthotic or prosthetic devices. If you see what we mean, developing layers that can perform as trusted collaborators, which includes, very importantly, being able to explain behavior. So these agents are supposed to be able to explain behavior of themselves and of others. And, well, this is the area, I suppose, is called the computational cognitive modeling. There are many kind of subdivisions even within that, but once again, if anybody is interested in this side, we will go to that in the question period. So agents and understanding. So human-level layers must be able to, among other things, communicate in natural language, understand the situation, the task, the domain, and the roles of self and other team members in a team of human, well, I could say robots, but it doesn't need to be embodied. It could be an embodied agent or a disembodied agent. It must remember relevant past experience. This is an extremely important part. It must be able to learn by being instructed in natural language. You know, a one-turn or even zero-shot learning. You see, there is no training. You see, this is the whole idea. But this learning is different from learning that most of you have been probably learning about. And extremely importantly also, they must be able to explain why they do what they do, why they make decisions that they make, as well as decisions of others. So I will show you a picture of the architecture. Don't get frightened. It's like too big. This is the entire architecture. I will go through this very quickly. So the idea is that the agent, the WM is working memory. This is long-term memory. It has inputs from language, utterances through the speech recognizer, but also has other channels of perception: oral, visual, tactile, olfactory, interoceptive, all of these types of things in principle. And what happens is there are interpretation parts of perception in general and natural language understanding, as a result of which what gets produced is meaning representations, text meaning representations or TMRs, or meanings of other percepts, like visual meaning representations and so on and so forth. After that, what happens is the newly perceived inputs are sent to something called the attention manager, which adds optionally goals to an active goal agenda of the agent. Then goal selection occurs and an active goal instance is established. Then a plan is selected to achieve that goal. Active plan instance get instantiated that way. The planner itself starts to work, and what it ends up at, like at the terminal level of those trees, to give you a simplified statement, there are choices of at least 3 different types of action. The physical action, well, motor action or physiological action, because that's also an action. If there are some types of artificial intelligent agents that actually simulate physiology, and so on. Verbal action generator, that's something that we kind of know more about. That's the text generation. And also the mental action generation, because there are quite a lot of results of understanding that do not immediately lead to outward expression. So you can infer various things, think about new things, and remember new things, and even learn new things. And all of that is done through this mental action generator. Now, this is the set of processes. Now, what it relies on in a very venerable tradition is on large knowledge bases. So there is The long-term memory, the semantic part of it, what used to be known recently as ontological models of the world. So object and event types, models of self and others, goal inventory, and language-related resources, things like grammars, lexicons, and a large number of specialized rule sets in our environment organized in something we call microtheories that Marge will be talking about later. There is a set of episodic memories, which is memories of remembered object event instances. Everything here, different types of meaning representations that have been obtained from various processors of perceptual input. They are remembered here, and these are sources eventually for analogy-based reasoning. That should be somewhat more familiar to many of you, because that's where machine learning in the understanding that people have goes on. And, well, there is also, very importantly, a situation model, people who are dealing with discourse processing and pragmatic processing. We understand what it needs. It's active physical, mental, and verbal object and event instances in their property, something which is active during, for simplicity, let's say, in this particular instance of a dialogue. So all of this needs to be developed somehow. All right. So the natural language understanding, as you can see, is outside of this whole architecture, but it's not true. In fact, our language analysis also makes use of most of the same memory models. But I will not talk about this. This will be left till later. Now, why do we need understanding rather than string manipulation using empirical methods? I can talk about this for hours, but one example is, well, you know, the Vinaigrette schema challenge. You should know about this. So the idea is, when you read this sentence like, the city councilman refused the demonstrators a permit because they feared or advocated violence, we need to understand who advocated violence and who could fear violence, right? And that is something that is difficult to do by matching examples, all right? So just one example. Once again, if anybody wants to talk about later, we can talk about this later. This is just one slide which I decided to include to show that the methods that we use are in service of the tasks that we are pursuing. Because what we do, in fact, is not method-oriented, it's task-oriented. It's not like we say, okay, we have this mechanism, let's see what we can do with it. It's the opposite. Here is the task, and let's see whether we can, by hook, by crook, somehow get to it. So it's not easy pickings. It's hardly easy pickings, but you see a methodological orientation at low-hanging fruit, currently prevalent in computational linguistics, will not advance our goals, you see, because our task is basic and very difficult. So this is our slogan: enough with the low-hanging fruit, how about some slow-moving meat? Right, so that was supposed to be one joke that I have in the entire presentation. Okay, so the overall task is complex. We are a relatively small group and have been for quite some time, so we need strategic simplifications to make certain things happen. So what we do is we, among other things, focusing on actionability of interpretation of percepts rather on deriving a perfect interpretation of inputs. So let me give you just one hint. Why do you think we, in dialogue, when we talk with other people, very often we interrupt one another, not only because we are impolite, but because we understand what other people want to say well before. Yes? So we do that. We have an interest in having agents that understand that too. You see? Modulo of mistakes, obviously, because we as people are bound to make mistakes in such situations too. But by and large, we don't. You know? All right, so more features. Modeling functionality is in an integrated rather than strictly modular fashion. So in our agents, NLP does not, or natural language understanding, does not bear the entire load. We want to bring in inputs from other sources, including memories, including not only immediate precepts. Okay, language phenomena are treated at those points in the process of analysis of language inputs, where chances for resolutions are maximized. So we are not interested in showing that in some cases you can resolve referential ambiguities during syntactic analysis, because in many cases you don't. So we're interested to do it when the chances are maximized. This is what's written here. And this is another very important point. We never expect any knowledge resource that we have to be finished, complete at any time. So the learning of ontological concepts, new ontological concepts, and new words and phrases, especially phrases very importantly, is something that should be brought into as a regular part of the repertoire of such an agent, because we don't want to have to always have only manual acquisition of knowledge. That will not work, right? So what we need to do is to have a certain critical mass of knowledge at the beginning, and then hope that something will happen afterwards. Right, so can, as we propose, really work in applications? Yes, we have been working on two, well, actually more, but two more advanced applications. One of them was called Maryland Virtual Patient. It was a disembodied intelligent agent for teaching future physicians to diagnose and treat diseases using interactions with a virtual patient, talking with a patient. So this patient had these capabilities. It could understand natural language, not completely, but in a rather broad way. It also had interoception. Understand what that means? It's a model and a simulation of a physical state. So if I have a cough, we built a physiological/pathological simulation model, very detailed, for the set of diseases that we were covering. So interoception is perceiving your own state. And that, by the way, how this particular agent decided to turn to the physician to actually, make an appointment to see the physician. It was different instances of agents that had different character traits and different kinds of diseases, and even different versions of the same disease that we imparted to them behaved differently with respect to when to present, as they say. Also, these agents, here, this is what it said, decided when to consult the MD, deciding whether to agree to an intervention. Some of these agents or instances of this agent were very suspicious about what the physicians wanted to offer them, sometimes for good reason, because the system was built in such a way that under certain conditions, the trainee medical student could really run this particular patient into the ground by, I don't know, deciding to lop off the arm when he had a cough or something. It was not. It could be done, but you see, there was a need for the patient to agree to an intervention, and also these agents could do certain actions, so verbal, dialogue turns for describing symptoms, and understanding interventions. Because you see, the idea is that probably none of us are very good with medical terminology, right? Yeah, okay. I need to be faster, you see, because this is just the preliminaries. So I need to leave the stage. Learning, it did learn new words and phrases, this, especially the medical terminology. Right. And outside of the cognitive model, changing physiological model parameters to follow progression of disease and healing. This was also a part of what was needed. You see, we needed to have a reasonable subset of the entire cognitive architecture to work in an application. So salient functionality, integration of different perceptual inputs, interoception plus language, and static knowledge resources and virtual patient's decision-making heuristics. Heuristics are the core issue of the whole thing. So the virtual patient system runs an ongoing commentary describing reasons for its decisions in terms that make sense to people. So we have a video demo. If anybody wants to see a video afterwards, we can show you a video. It's, well, okay, it will not get an Oscar, but it's good enough. So another more recent application is a human robotic team working in the domain of assembling Ikea furniture. This is not, we didn't invent this application. It's like something that people do. So at the outset, the robot knows how to recognize an inventory of objects and perform a set of primitive actions. You know, this is grounding. We will not go into that very much. And then what it does, it's run through a sequence of primitive operations with a running commentary by the user. The robot understands the meaning of the utterances and uses its reasoning capability to generate an hierarchical organization of actions for the purpose of building, let's say, some piece of furniture. What used to be known as a script in old terminology. As a result of the learning process, learns new complex events or scripts, names them. That's an interesting part because they're not always named. Determines their constituent sub-events and their participants, determines the events in which they are sub-events, and records this new knowledge in its memory, specifically in the ontological world model. So just 2 slides to show you some formalism. You don't need it. But what I'm trying to say is this. Remember, in the diagram of the cognitive architecture, there were several kinds of input from language and not language and so on. So in order to facilitate the reasoning with them, we need the outputs of the understanding processes to be formulated in formalisms that are compatible. And that is a part of our job, and this is what we did. This is the result of, like, I built a chair. It's a subset of, actually, it's in reality much more information. So this is the result of a text meaning representation, and this is the result of a visual meaning representation recording that the agent saw the human assemble the chair leg using the bracket and the dowel. So this is the results, but mind you, we do not do vision ourselves, we import it. What we do is we take the formalism that is output from the vision understanding system, which is not in this formalism, and we understand it, right? So, for instance, it's the similar thing is if you have a speech-to-text component. So if there is some speech, and then you just get the text, it's not the final result. On the side of the vision, there will be some spatial representation that people do as a result of vision processing, and we can convert it into a representation which is compatible with our text meaning representation. So it's just to show that there is a lot of work at the preliminary preparatory stage. All right, so at this point, I stop talking, and it's your turn to. This is now the real content of the lecture.
Oh, right. Good. Okay. So as you saw, the language component is really kind of very small on this big architecture, right? But it doesn't make it any easier. We still have to do all of language. And one of the important things we believe about language processing is that we will never get to coverage of really all of language if, like in the old days, people built expert systems and each expert system only did a little bit of language. Because each of those little bits of language are going to be the easier little bits of language for that expert system. So we really believe we have to look at all the complexities of language together and figure out where everything fits. And then when we're actually making an application, we can, of course, make it smaller what we actually cover. But the idea is to cover everything in principle. So what we mean by natural language understanding, well, creating the meaning representations like on the right-hand side. You've probably seen representations like that. It's just basic frame-based representations. These are ontological concepts in jest. They have properties, agent, theme, time. They have instances of ontological concepts as their fillers. The actual meaning representations we generate have about 10 times more properties, but the properties are of this type. They are metadata for developers. So we can trace why every single decision was made. So the idea is that this meaning of eat, ingest, came from the lexicon sense, eat V1, the first verbal sense. It's the third number, and there's lots more information, right? So none of this is magic. It's all based on a very complicated lexicon that looks like this. So for example, for C, we have a whole lot of entries, but this is just a quick example. The first one is to perceive visually. He saw a new car. This is to consult with for advice. Grandma saw her doctor. This is to refer to a portion of text. For details, see Chapter 4, etc. Each of these has a syntactic expectation. That's basic transitive. This one has to be an imperative. It's a verb form imperative, etc. So the idea is we're taking a syntactic representation and mapping it onto the semantic representation. So here the agent of this involuntary visual event will be the meaning of whatever that syntactic element is. I assume you all have had enough background to get the gist of this. And the reason why we can do natural language pretty well, at least for some things, is that we don't back off of doing this. We know that a lot has to be recorded in the lexicon. So sort of like construction grammars, we have a lot of expectations in our lexicon. The lexicon currently is around 60,000 senses. We need it to be about 10 times larger. We know that. And so we're working within this constraint, but still we're going after real sort of coverage. So Sergei mentioned the term actionability. Hold on, sorry, actionability. So the idea is that we're trying to get the agent to a point where it understands an input enough to do something useful with it, which might not be a full understanding of the input. And since we're trying to make language understanding emulate what people do, we have two notions of incrementality. So horizontal means that we have the agent take as input little constituents one at a time, right? So first, the noun phrase, a duck was swimming in the water. We're not having the agent try to semantically analyze the word the. That doesn't make any sense, right? So there's some notion of incrementality this way, especially if you have an agent, for example, that has to act quickly on inputs, right? So grab the fire extinguisher and the agent should be going to the fire extinguisher while it's listening to what has to happen next, right? We also have a very important notion of vertical incrementality. That's this. So we have 6 levels of depth to which an agent can understand any input. Actually, any increment of any input, right? So essentially, you can be going up and across and down to any degree at any point. So let me just quickly go through the stages. We'll go through them more in depth. Pre-semantic analysis, integration, basic semantics, basic coreference, extended semantic, situated reasoning. So basically, these first 5 are what we might think of as general natural language understanding before an agent is in a domain that it knows really well. That last one is a big leap because the agent has to have a lot of knowledge of the domain to carry out the last bit. Okay? So this is just a schematic of essentially how the actionability works. I won't get into too much, but the idea is take the first constituent, process it as deeply as you want to go. What is as deeply as you want to go? Well, the agent makes decisions based on its plans and goals at any of those depths of analysis. So the idea is that reasoning about the task, about the goal, is actually threaded into natural language processing itself. They can't be separated. Okay, so pre-semantic analysis. We use an external engine for this. Why? Because they exist. So it's basically morphological analysis and syntax. The engines exist. We're using the core NLP tool set right here. And because we don't want to spend any more time in life doing syntactic analysis. That's not our interest. We use the results of syntactic analysis to inform semantics. And we don't really care if syntactic analysis is wrong, because we have ways of trying to recover semantically from incorrect syntactic analyses. So this is both theoretically motivated and practically motivated. Since these tend to be quite error-prone, particularly for dialogues, we use we use the lower constituents, not the entire parse, as input to semantics. Then we have to integrate the output of any external engines. People don't like to think about how hard integration is of external components, but that actually takes a lot of work. So I'll show you the 4 aspects of that. So first is syntactic mapping. We have to take the words of the input and try to map them to the syntactic expectations in the lexicon. That's straightforward. In this case, it works. So eat V1 is a good match. In this case, eat V2, which is the phrasal to eat away at, does not match because it has 2 unbound prepositions, right? So that's basically what happens in syntactic mapping. And we can end up with 1 valid map, with more than 1 valid map, all kinds of eventualities. We'll get to that later. And we can also end up, by the way, with no valid mappings. This often happens when you have unexpected input, bad syntax, which is essentially what we all speak in all the time. So if we take regular dialogue, regular speech, put it through a syntactic analyzer, you'll get incomplete parses for practically every sentence. So what do? Well, we take responsibility for it, and we try to recover. So we have lots of methods of trying to recover from unexpected syntax. Things like stripping away repetitions. So this is actually from a real corpus. Okay, it should get there at 2 a.m. This will create havoc in your parse. We try to strip it away and get a proper parse. If after this recovery we can get a good parse, great. If not, we can recover further in ways I'll talk about later. But the main point here is simply that we're taking responsibility for everything. We really fundamentally believe it's not the right thing to do to build a theory that works as long as something that doesn't yet exist will exist by the time that our theory is used. So we're trying to back away from that. The beginning of new word learning. There are a lot of words that we don't know from our lexicon. So therefore, for every part of speech, we have templates that can accommodate different syntactic and semantic expectations, and so we do the syntactic portion of new word learning right now. Then we re-ambiguate decisions that syntactic parsing cannot make. So PP attachments, you all know these examples, right? That's not a syntactic matter. It's a semantic and pragmatic matter. So only vision can tell us, really, what's going on with this usually. Nominal compound bracketing, preposition versus particle ambiguities. These are all not the job of syntax. We re-ambiguate and let semantics try to solve the problem. Now, an important thing about trying to do analysis of real sentences is combinatorial complexity. And this is a made-up example. It's supposed to be sort of funny. It's not real. But even if you only had 2 senses for each of these words, you're going to have 128 candidate interpretations. That's a lot. So one of the things that we allow the agent to do, don't force it to do, but allow it to do, is it can, even at this point, merge analyses. So we have 2 different ontological concepts, pirate at sea or intellectual property thief for thief. It can go ontologically up to the next level and give us the more generic interpretation. Why? Because we would want to do this in part because of the human collaboration in this whole process when we're building this. Because you can't, as a human, look and try to debug 128 of anything, right? So we're trying to make this so that we can actually usefully debug things. Also, perhaps for our agent, it doesn't matter which kind of thief you had. Thief is good enough. So again, we're trying to be really practical in how we approach things. But this is all, of course, automatically done. Okay, basic semantics. Everything that can be done using lexical senses, their ontological mappings, and of course the information in the ontology, and a general approach to meaning composition. And it covers a lot of ground because we have a lot of multi-word expressions, including constructions, and we have what we call procedural semantic routines, which are functions that get launched from the lexicon for things like respectively. John and Peter ate spaghetti and a sandwich respectively. Well, that's a procedure. Who ate what has to actually be figured out. So we can do that all at this stage. And these are just some of the phenomena we cover. Indirect speech acts, conventional metaphors, lexicalized metonymies, nominal compounds. Several types of ellipsis we actually can either fully or partially cover at this stage because of expectations, again, in the lexicon. Just to give one example, verb phrase ellipsis, constructions, John ran as fast as he could. To do something as fast as one can is a construction. Based on simply recognizing that construction, we can actually reconstruct the elided meaning. By contrast, for regular VP ellipsis, John had a nap today, but Henry didn't. We can realize there's an elided event here. We wait till the next stage, reference resolution, to try to figure out which one. So the point here really is not the actual inventory here, but the goal of taking care of all phenomena. Rather than having one person taking care of pronominal reference and somebody else taking care of nominal compounds, we're really trying to make a whole story of how you take care of full semantic analysis of all things. Then basic coreference, which we actually do use statistically trained coreference resolvers for what they can do. They can't do everything, obviously. They help us with the easier ones, pronouns, definite descriptions, proper names. We add functionalities for many of the harder ones, like broad referring expressions. I started jogging every day. I should do that too. Mainstream NLP has not made it to these yet, and we go for some of them. We can't get all of them, but we have a microtheory that actually gets us a lot of them. Third-person pronouns are notoriously difficult for statistical methods because everyone acknowledges you need semantics. We can catch a lot of those at this stage, basic coreference. We can actually get more of them down here. So again, we're taking care of things as we can. More about basic coreference. You probably all know this literature to some extent. You have to know which kind of relations are not coreference. Our flight was nice. The landing. Why the? You have to figure that out. Again, these are typically handled by different people in different publications that do one publication and then stop work on things. So putting this together as a puzzle has really been interesting to try to take care of. Then extended semantics. So extended semantics adds more generic, that is not domain specific, knowledge bases and reasoning rules to try to deal with some of the residual ambiguities. We still are going to have a lot of ambiguity here because, again, we haven't yet completely integrated into the context. And incongruities. So things like metonymies. The red hat said hello. Right? That's a metonymy. It's the lady with the red hat. In our basic analysis, there will have been an incongruity. This does not fit. We have to add more reasoning to reintroduce the lady into the context. So we have lots of rules for basically knowledge repositories that help us to do this. So there's ontological patterns for nominal compounds. Lateral selectional constraints for lexical disambiguation. There's a lot of, yeah, I can do that. The second one, you mean? Yeah. So, okay, lateral selectional constraints. This is an interesting one. If you think about an example like the police arrived at the port before dawn. They arrested the pirates immediately. Okay. We know which kind of pirates we're talking about, pirates at sea, because the police arrived at dawn. But the police they arrived at the port. But the fact is, the port, the key bit of information that we need to know which kind of thieves we're talking about, not the intellectual ones, the ones at sea, was in a different sentence. It was not in the basic dependency structure that would inform the disambiguation. So the idea is, how do you establish a general ontological context for the entire text? Well, we actually have several very concrete methods of doing that. You see in the literature, just use the context. And we've tried to formalize what using the context means in terms of specific ontological search functions that would do things like associate a port with a pirate. So, rules for interpreting metonymies, I gave you that example already, and dialogue analysis strategies for integrating the meaning of fragmentary utterances into the discourse. These are things like, John swam all day, period, really fast. Okay, you have to get the really fast, again, put onto the previous sentence, and this uses dialogue expectations, dialogue structure expectations to actually do that. Then we get to situated reasoning. This is where all of that agent architecture that you just saw comes into play. This is where the agent knows what kind of plans it is pursuing. It knows which scripts it is in. It has an idea of what its interlocutor is trying to do. And this is the only place where you really can do certain aspects of language understanding. So if I said right now, I'm hot, right? In different contexts, that would mean different things or could mean different things, and that is not a linguistic issue. That is an issue of the agent actually being in a context and understanding what is going on and what the abilities of other people in the context are, like how they could actually help that situation. So what happens here? Well, the first thing that happens here, kind of formally, is we cobble together the meaning, of syntactically irreparable inputs. Remember up here, during this pre-semantic integration, we looked at parses, syntactic parses that were bad, and tried to fix them, okay, to make them actually good parses. If we failed at that and we have a really non-canonical input, like a really syntactically bad input, what we do is we skip this whole middle section. So basically this is kind of like the bag of words situation, right? It's just almost garbage. We go right down to here and try to cobble together the meaning exclusively semantically. Right? So take all the meanings of all of the constituents we can find and simply try to put them together in some way that makes sense to the agent based on the context and what it's trying to do and what it thinks its interlocutor is trying to do. Here's a big one, using domain-specific preferences for lexical disambiguation. So in terms of like our chair building thing, the word chair can mean either chairperson or a chair you sit on, right? So here we're going to prefer chair. But very importantly, we're waiting till the end to prefer chair. Because if we just say from the very beginning, oh, we know what domain we're in, practically the entire problem of lexical disambiguation goes away. We'll never address it because a lot of the decisions will be made based on the context. And even if you can imagine some contexts in which, yeah, we really do stick to the topic, humans don't stick to the topic. Humans are always going off into different topics. So we really think that the way to handle this is to wait really until the end, figure out the general linguistic analysis, and then at the last moment, and again, the last moment is within like a second of the rest of it. We're not waiting for a year to think about this. At the last moment, make these domain-specific preferences. Here we make the final decisions about speech act interpretations. So indirect speech acts, I don't know, I want a sandwich. Is that just a fact, or is that I'm asking you to do something? Again, only here can you do that. Detecting non-canonical indirect speech acts. So earlier, based on constructions in the lexicon, we could detect that there was a possibility of indirect speech using things like, I would really like. Now we know that could actually be a statement or a request. But there are plenty of times when you actually say something that's not using a typical construction that you intend someone to do something. So, for example, if I say, oh, the mail just came. Maybe I want you to go get the mail, but that's not going to be a construction that tells you about that. You really have to understand the situation. So we try to detect those here. And then further specifying the meaning of new words. So before, at this stage, when we find a new word, here we do the syntactic representation of it. Here we try to get the basic semantics, that is just using the ontologies. So for example, if we have, I ate a kuapaku for breakfast, you probably don't know that word, I didn't either, but you know it's some ingestible something, right? So at this stage, we could figure that out. Maybe at this stage, we have more information to learn more about what that possibly could be. So we do more about new word learning here. Okay, what else do we do? Situated coreference. So we all know the problem. You point at something and say, give me that. And linguistics doesn't have anything to say because this is the vision guys that have to come and help us. And as Sergei said, what they need to do is take the output of the vision apparatus, convert it into meaning representations of the type that are compatible with the agent. And so therefore that's what has to happen here. Making implicatures. So he issued that command abruptly might mean that he's angry, or it might not mean that he's angry. But again, this is the stage in the processing where implicatures could actually be important. And then deciding what to do if the input is still not actionable. Okay, so by this point, we already have some meaning representation. Maybe it doesn't account for everything. Maybe some of the words are underspecified because they were unknown, but we have something. So the agent's question to itself is, can I do anything? Was it a question? Can I answer it? Was it a command? Actually, questions and commands are the easier ones. The more difficult ones are what look like a statement, which could be simply a statement, or it could be something indirect that you were supposed to have understood as not a statement. And as you all know from basic computer science and interface technologies, we can't have the agent always asking, should I do something about that? Do you want me to do something? You would drive your interlocutor crazy. So we have to actually be really careful about whether we're doing anything formal, except remembering about things that are not overtly actionable. Okay, this is just, as Sergei showed you some formalism, this is actually a different, the actual output of a TMR, a text meaning representation, for he wants to play. I'm just going to give you a couple of notes about what it is. So we had 25 candidate text meaning representations, because I said there was ambiguity, right? So this whole process was trying to get rid of ambiguity. So since, like, the word want has a lot of senses, the word play has a lot of senses, he has, I think, 2, human and animal, right? So there are plenty of senses here. Right, these are the ambiguous words. We have, again, this is metadata for us to try to figure out what's going on. So we know that in different versions, you're going to have different options. This is the basic TMR that we saw before. Then we have a whole scoring mechanism. So syntactic score, semantic score, combined score. So again, it's a lot of metadata for us. And the idea is we got down from 25 candidates to 2 candidates using all these methods that we just talked about. This did not involve that last stage of situated reasoning, so we couldn't get any further than thinking he wants to play either a musical instrument or a sport. And we could not get that disambiguation. But again, in any kind of an application, maybe our particular agent doesn't even care about anyone playing about anything. So one of the types of action that an agent could take is remember and ignore and don't do anything. So don't do anything is a really important action for an agent to have. Oh, okay. So this is Sergei mentions saying something about modality. We do, among the many microtheories that we have, and microtheories are just sort of holding bins for dealing with a topic, right? So verb phrase ellipsis is a microtheory, and nominal compounding is a microtheory. And for us, modality is a microtheory. So essentially, modality, as you know, is a meaning that scopes over propositional meaning. And so the idea for us is that the modality type volative he wants to play, it's volative modality with a value of 1 on the 0 to 1 scale, whose scope is playing the musical instrument. And the good thing about our modality approach to modality is that you can have embedded modalities as well as modalities interacting with aspect. And so the microtheory of modality actually covers all of that. Is that what you had in mind? Yeah. Okay. So this is the final slide. I know some of the types of linguistics that you all do here. I've read about the prog dependency grammar and the tree bank and all kinds of things. That is obviously one direction for linguists in the age of AI. It's a very important one to support supervised machine learning. That's obviously not what we're doing. Although I think that if we ended up with enough TMRs, the machine learning people might like that as input. Who knows? Maybe. But so what I see sort of as my future and future of people who'd want to do this more integrated type of agent building is improving the coverage of the microtheories for all the linguistic phenomena. I just touched on a couple here. We have papers on many of them, but in all cases we've done some, and you could go deeper and deeper and deeper. So that's really all. And the real key to that is that what we need is we need computable heuristics. And that's what you don't find in the general descriptive linguistic literature, right? So a key example here is if you have a theory of discourse that relies on the notion of topic and comment, or theme and reme, but there's no formal way of detecting what the topic or comment is, then that theory is not going to be computable. So from our perspective, you have to have computable heuristics, or simply whatever you're doing is out of bounds. So a question is, what can be gleaned from the existing non-computationally oriented literature? It's an interesting and I think big question. Developing methodologies for organizing and prioritizing manual and semi-automatic knowledge acquisition. This is a big deal. You all know about the knowledge bottleneck. It's basically what killed knowledge-based approaches to doing natural language processing, saying we need too much knowledge, it's not possible to acquire it. That being said, I would suggest that artificial intelligence of this type integrated into agent reasoning is not possible without this. So therefore, rather than having a brick wall, you simply have work to do. And the question is, how would you organize that work to do? Another thing, in order to get any of this accepted by the field at large, which is not easy, is you have to figure out how to develop methodologies for evaluating what you're doing. Right? Because essentially all of this linguistic analysis, it exists in a generic way, linguistic analysis of any domain, but of course then you have to zoom in on some application in order to be sure you have all the coverage and things you need. And it seems to me it's important both to be able to evaluate the general approaches without 100% knowledge support and the more localized approaches. And then, of course, you've got what I think is a really cool thing, working with the vision, robotics, and speech recognition people on making on integrating their results with our results. So essentially, language understanding should help the vision guys to figure out whether they have X or Y if it's partially occluded. And they should help us figure out if we didn't hear something correctly, kind of what is going on in the visual space. So making this all interactive rather than strictly modular, I think is a really interesting direction to go. And that's it. So, thank you. Do you want to come back up for questions?
Well, thank you very much for your interesting talks, which I think in many points are very close to what we are engaged in, not in such a overall picture, but with some particular points you have made. So I hope that we can start an interesting discussion, questions, points, objections, if any. Yes, please.
When you mention microtheories, this immediately reminds me of psych. Did you have a look at psych microtheories or similar, say, traditional resources to leverage on?
Right. Well, that brings up yes. The quick answer is yes. But the problem with psych, we have kind of two problems with psych. One is that anytime you have a resource external to yourself, the amount of development, not research, but development time it takes to import it is massive. And so therefore, in a group of our size, we actually concentrate much more on the science than the actual development. So on the research and development spectrum, we like to be more toward research, and they're obviously more on development. The other kind of problem that we have with psych, although, by the way, I'll say for myself, and I think it's for both of us, absolutely great that they're building it. You know, like great that someone is taking seriously the fact that we have to have all of this knowledge. Terrific. But the way that they've organized the knowledge as a sea of assertions makes it very, very difficult to use. And so therefore, unless one were to become an expert in that particular resource and really learn, I mean, they have millions and millions of assertions that are not organized in a very human, accessible way. So that, to my mind, is a whole other research project to try to figure out how you could use that resource. And by the way, the same with many other resources that in principle could be very useful.
I remember that we were tasked by one of the funding institutions at one point, like late 1990s, to write a report about how good the language support there is. And one must say that for Doug Leonard and company, the language part was kind of an afterthought. So that was, for us, it's the opposite possibly, because we came into knowledge representation and acquisition because we wanted to do these types of modeling, right? But I know, for instance, that there are some groups who themselves don't do language work, who use the publicly available subset of psych in their work. Like, for instance, Ken Forbus's group at Northwestern, right? It's not anything really outstanding from the language point of view, but they don't have it as their goal, you see. All right, so, well, I will just...
But Ken Forbus is also, good for him, almost a specialist in incorporating external resources. So he spends a lot of time and he really knows how to do it. So I think if you're going to do it, it's good if you're a person who has that experience.
Yeah, he's a hacker. He does it himself till now, so anyway.
Thank you. Some further questions?
Who's going to say we're crazy?
It's easier for me for more questions. First thing, when you compare your approach with say shallow AI based on neural network and so on, when you mentioned this evaluation, do you envisage some kind of unbiased experiment comparing your artificial patient with some chatbot powered by machine learning AI? It's kind of baseline comparison probably because you have a lot of huge knowledge base. But anyway, is it something you also envisage?
Yeah, it's a really good question. And by the way, we've spent a lot of time thinking about evaluation. It's one of those like monkey on our shoulder type of things that we can't get away from, right? The thing is this, that in my view, those methods are good for a completely different set of tasks than our methods are good for, right? And the thing is, I don't think that we could ever set up a really fair competition. Even if we were to say, okay, 30, 50 years from now or something, yes, have both virtual patients. But here's the difference. Our virtual patient will be able to explain everything it did, why it did it, all those kinds of things. Theirs won't. So say theirs is a tad better, but ours can explain. Who wins? You see what I mean? So I don't really know how you can. It's so hard to compare. It's really hard to compare.
This is my third question.
Okay.
That's why whether you think this approach could also be paired with this shallow AI to provide explanation, which is what usually say the traditional communities views as advantage or opportunity in the current AI world.
Right. Yeah, I don't think that, and I'm not an AI, I'm not a machine learning person, but having talked to plenty of machine learning people about this, I don't think that those methods will ever be explainable. I mean, even if you could like put our type of system on top of it and pretend it was explaining it, it's not going to actually be explaining what's going on. That being said, for our purposes, there's plenty that we would love from the machine learning community that we're not yet getting. But we see machine learning as serving us rather than us serving machine learning, right? I would love better syntactic parsers. I would love to actually be able to rely on a syntactic parser, and it's not happening. So basically, our approach to syntax is to use very little that we can rely on, rather than, wow, it would be great to be using the highest node if it were correct, right? So that and many, many other things, I could make a whole laundry list of things I want from that community, but they're not interested yet. So I hope that things go in that direction.
So the actual engines for decision making, right? Once you establish the features, right, which those people in machine learning tell this is what linguists must be doing, citing, Chris Manning and such people. We actually have implemented in the virtual patient system a regular heuristic set of functions like old style that we could be doing, and also something else based on influence diagrams with Bayesian reasoning, right? So when we had to really do the priors and tweak the priors and so on. So from some point of view, that step could be actually done by several different methods. What we think is that the theoretical and descriptive part, well, I don't know, you can call it feature engineering, but that is kind of the format of the output of theoretical and descriptive reasoning. Well, that could be kind of used in different ways. The preliminary, though, is still, in our view, required.
And I think that sort of in terms of practical applications, like especially the really serious ones, like how to invest your money, which cancer treatment to choose or whatever, it would be really interesting if the statistical methods would do their stuff and get an answer. And what if we came up with the same answer by the our methods, right? Our methods could explain however our methods could, but these methods would be backing us up on a lot more data. You know what I mean? If I had to make that decision, it'd be nice if you actually had two sources of knowledge supporting it.
Before somebody else wants to ask a question, I have a kind of linguistically rooted question. When you display the blocks, then you start with some kind of syntactically based representation and go through several steps through the basic semantics and upgraded semantic. I expect that the structure of the representation is to be changed when you go through the steps. So how do you change the structure? In which way you change the structure?
Well, we add features. So essentially, for us, the text meaning representation with the concepts is really the only, that's the core of it. So the syntactic heuristics that we use to get there, they're kind of outside. It's all still in a structure that becomes very, very large. So what happens is we keep on adding features to the feature structure. In some cases, well, in many cases, we'll make a feature more specific. So for example, say we have a nominal compound that's not handled at the first stage of semantics by the lexicon. So it's not something like attorney general, which is just listed. So we have something like, I don't know, screen string. Okay. So at the level of basic semantics, we simply have screen relation string. But then later on, we try to make this relation more specific. So later on, we would then switch that out for a more specific relation if we could figure it out and change it in that way. Same thing with things like coreference. We add in a coreference slot that then might actually make something more specific or however it is. So we just add to the feature structure, but by the end, what the machine has access to is like that large.
The methodological is largely in the ontological world model. You see, we have, in our model, we have something like 450 basic properties, over which we get, because concepts are essentially main collections of properties with narrow
selectional constraints.
Sets of values, right? So those are undefinables, the 450 above elements. And then there are indeed some microtheories, like for instance the formulation that we want to use, like, let's say we saw the modality, but there are many others like that. Usually it's clear because we want the basic meaning and then those kind of parameterizable parts of meaning we want separate. So, quantification will be, which we don't stress as much as formal semanticists do, but it will be a separate thing. So if we're talking about the meta vocabulary, then the feature and values, the inventories are defined separately. Right. And we keep, for whatever purposes, the syntactic structure, but we kind of don't use it in the later stages.
And one of the important things we think, again, tactically in large part, is that we often at the beginning have an underspecified representation, like especially for things like ellipsis. Like we know there's an event, but we don't know which one. And we actually have a microtheory that can deal with a lot of the co-references, but certainly not all. You can find examples where it's so difficult, even for a human, to understand. And so we think we can get away with actually leaving it as underspecified event and see what happens. And so that's one of the strategies to push this research forward, is to be practical in that way.
I think the artist wants to say something.
I have a question and a comment. So, if you are pushed to say to which of sort of the existing theories of semantic representations or existing semantic representations the TMR is sort of closest to, or at least in some features, because you presented some examples. I understand they were very much simplified. Yeah. They were just a one-level set of attributes and values. But there are many others. There is CCG, AMR,
ours is
MRS.
Ours actually is that simple. It is always going to be just the simple slot formalism, but with more properties possibly. We gave you simple examples, but the formalism itself doesn't get any more complex than that. And we actually believe it needs to be that simple in order for humans, regular humans, to be able to sort of interact with it.
Okay, so it's like it reminded me of the frames from the early information extraction system. So that's a fair description.
Absolutely, because you see, from many years ago, like over 30 years ago, I decided that I stopped paying attention to arguments about formalism. Because for a long time in semantics, it was my sigma is better than your lambda. Okay, which is not important. What we stress the content, we stress the actual lexical semantics and the meanings that we represent with our set of features, right? And we manipulate them with whatever analysis is needed, and we're, I must say that when I read all these things, well, to me they sound extremely narrow and primitive. Those complex formalisms, and they concentrate on 2-3 phenomena. He wants to marry Norwegian. Well, I'm very well prepared for our system we can do it. But there are ways of doing it. So, as I say, I don't think that we have a good parallel with any of the formalisms. But if we are saying, okay, can we represent this as different from that and that and that, we can show you in every case.
There's one more thing to say, though. This TMR formalism, right, it is as simple as that always. However, when we write things like scripts, so the ontological scripts that actually created the physiological simulation of a virtual patient, that was not just slot filler formalism. We obviously needed programs. And so therefore there is a distance. I mean, we can, in our formalism, not exactly that, take care of any knowledge representation, but it won't look exactly like that. And we've thought long and hard about whether we can have an ontology writing formalism that is so great that we could have a generic program sitting over it and have everything work out correctly. But that, we realized, is really trying to create programs that write programs. So we haven't gone down that direction.
So there is and that is the TMRs is just one part of the formalism, because for us, the knowledge resources, the vast knowledge resources, occupy a huge center stage. So our lexicons are complex, our ontology representations are complex, including things like monody, on events and on objects, not just on objects. So from the point of view of expressive power, we need to look, I think, we need to look at that as a kind of in combination, right? So, because when I read, once again, every book or article on computational semantics, they don't talk about knowledge representation. I always make jokes about, well, having a model M, you're relative to model M, you interpret it. What's an M? No, it's a nice imaginary thing. We're descriptive people. We're just we sit down and we are saying, slow stuff.
No, I mean, my question was, I like, the simplest formalism, the better. But for some things, this very simple thing, I was wondering how that's, for example, scope things. Anything in, when you need scope, it's a little bit difficult to do in
Why?
just
Why?
like.
Yeah,
Okay. Maybe I should look more closely.
Clear, you're right, because those were just examples for, presentation. But what is a good exercise, if we one day have the just to show how we represent examples of those other kinds. Yeah. Sorry.
Okay, the comment, just a very short one. You said at one point that you think that even 30 years from now, the learning systems will not be able to explain. I actually believe they will, with mistakes as they do today with the non-explicable results. But we should get ready for actually comparing the thing in a complex way. You talked about evaluation. So I think, yes, the explanation should be part of the evaluation, especially in cases where you really need it, like medical diagnosis. But I think they will also be able to learn that. And so it might. I mean, that's very hard to speculate today. So yes, I mean, there should be. I'm sure there will be some evaluation at some point. I mean, maybe not the Alexa type thing, but something similar.
So let me comment on that. This is a very interesting. Okay. It's a very interesting set of points, but you see, there is so much to say about evaluation in general and explanation. And you see, explanation, one simple thing to say, should be geared to a particular audience. You see, so if you describe what, I don't know, a violin is to a 5-year-old, and you describe what some musical instrument is to somebody who plays a musical instrument, you, even from the point of natural language generation, you do it differently, right? And when you explain, we actually went into this in our, to a degree, in our virtual patient thing, because okay, so across our patients, there were parameters, personality parameters, that had to do with the level of specialized medical knowledge for these people, agents. And so when the physician is describing some state of affairs to one kind of person, another kind, it should be different. So understanding this is in itself an issue. And also, once we probably haven't yet gotten into, we being the field, into this explanation deeply enough. I'm curious about, it will be very difficult to define what constitutes a good explanation, right? Well, you can give people a test afterwards, but there are so many layers of explanation and angles depending on why you need an explanation to agree to a treatment if this is a medical situation, or in order to be able to teach students something. So that's one. And another thing is, on a slightly different topic about the evaluations, we are at a disadvantage, all of us, because what we really need is to wait till a comprehensive system of this kind could really be kind of used in a broad application with expectations that are deep. So we cannot compete with partials, right? And it's good for applications like machine translation, where you can fake, you see, because you don't need to explain, you just have, I didn't think about this before, but now, earlier, but now I do. So evaluation, I don't know what the best thing is to do. But about the explanation, it's very possible that down the line there will be explanations from based on some kind of learning and comparison. Thing is that if you need something kind of unexpected in an unexpected dialogue situation, yeah, right. So
I'm afraid we spent our time. So I would like to thank again the speakers, and I hope this is not the last time we meet at this nice building, so to say. And So have a nice time in Prague. Still 2 days for you. And I just would like to announce the next session. Next week we will somehow cook in our own kitchen, so to say, and Maruška Mikulova and Jarmila Paneva will present results of the research. So I hope to see you here next week, Monday afternoon. So thanks again.